All right, so today we're diving deep into bohrium.
Oh, Bohrium.
Element number 107, BH.
Mm-hmm.
And you've given me some pretty interesting sources here. A mix of, uh, personal notes, scientific papers.
Yeah, I thought it'd be fun to kind of see what we could find out about bohrium.
Exactly.
A synthetic element,
Yeah.
which right off the bat is kind of fascinating. We're not talking about an element that you're going to find out in nature.
Right.
This is something that scientists figured out how to create by smashing atoms together.
So no digging in a mine for this one.
Nope.
This one's all lab created. And it looks like the story starts with some Soviet scientists back in 1976.
Yeah, a team led by Yuri Oganessian
Okay.
at the Joint Institute for Nuclear Research
Yeah.
in Dubna.
Dubna.
And they bombarded bismuth with chromium ions,
Okay.
specifically bismuth-209 with chromium-54.
Right.
And they believed they created bohrium-261,
Okay.
but it was unbelievably fleeting.
Fleeting. What does that mean? Like, how fleeting are we talking about?
It has a half-life of 1 to 2 milliseconds. So imagine trying to study something that is there
Yeah.
and gone basically as fast as you can blink.
So not something you can hold in your hand. And I'm guessing because of that short lifespan, there was some skepticism around it.
Oh, absolutely. Yeah. It wasn't actually until 1992 that the International Union of Pure and Applied Chemistry, the IUP,
Yeah, you peak. Yeah.
essentially the governing body for chemistry,
Right.
officially acknowledged the discovery. So you're talking about a over 15-year gap.
Wow. What convinced that? Was it just more evidence, or did somebody else take a different tack at it?
Well, there was a confirmation done in 1981 by a German team led by Peter Armbruster and Gottfried Munzenberg
Okay.
at the GSI Helmholtz Center for Heavy Ion Research in Darmstadt.
Wow. They definitely like to make those names long.
Yes, they do.
Yeah.
And they used a similar technique, bombarding bismuth-209 with chromium-54. But they created a slightly different isotope, bohrium-262.
Okay. So same element, slightly different atomic structure.
Exactly.
Was that more stable, or was there something else about that made it easier to study?
It wasn't necessarily more stable.
Okay.
But what they did is they very meticulously measured what's called its alpha decay chain. So basically tracking how it breaks down step by step.
Yeah.
And they were able to link it back to known isotopes of fermium and californium.
Oh, so it's like a family tree.
Yeah, like a family tree. And that was a really big piece of evidence to convince people, like, okay, this is really there.
Gotcha.
But then it gets even more interesting because even the naming of the element was controversial.
Oh, so there was even debate over what to call it?
Oh, yeah.
Okay.
The German team proposed the name Niels Bohrium
Niels Bohrium. Okay.
to honor Niels Bohr.
Right.
And they even suggested the symbol ENS for it.
ENS, okay. I assume IUPAC had other ideas, though?
Yeah, they actually preferred just bohrium.
This bohrium.
With the symbol BH.
BH. So a bit simpler.
And this led to a 5-year debate in the scientific community.
A 5-year debate over the name.
Over the name.
What was the I guess the reasoning for IUPAC to push back on Niels Bohrium?
Well, they argued that using a scientist's full name for an element was unprecedented and could lead to, problems down the road with other elements being named.
All right.
And also they were worried about potential confusion with boron.
Oh, okay.
Which is a much lighter element, very different properties.
Yeah, I wouldn't want to mix those up, especially in a lab setting.
No.
So did they win?
They did. In 1997, bohrium became the official name.
Bohrium, okay.
Interestingly, the Danish branch of the IUPAC actually voted in favor of the shorter name.
Oh, wow.
Perhaps a bit of national pride there for Niels Bohr.
Yeah, maybe so. Okay, so we've settled on the name. But what about the element itself? I know you mentioned isotopes earlier. Are there different versions of bohrium?
Yeah, absolutely. Since its initial discovery, scientists have created a number of different bohrium isotopes in the lab.
So isotopes are like kind of like siblings of an element.
Yeah, exactly. They have the same number of protons,
right,
which defines the element,
right,
but a different number of neutrons.
Like carbon-12 and carbon-14.
Exactly.
Same element, different weights.
Precisely.
Okay. So what about bohrium's isotopes?
Well, they've created isotopes with masses ranging from 260 to 278.
Okay.
But here's the thing. All of them are radioactive.
Okay.
And most of them have extremely short half-lives.
Okay, so back to that problem of studying something that disappears really quickly.
Exactly. You're talking milliseconds, seconds.
Now, I noticed in the notes that they're still using that that chromium-54 bombardment method
Right.
to create these isotopes.
Mm.
Why stick with that if they're so hard to study?
Well, it really comes down to the power and the precision of modern nuclear physics.
Okay.
These experiments are incredibly complex.
Yep.
They require huge amounts of energy to force those nuclei to fuse together.
Right.
But by very carefully adjusting the conditions, they can create different bohrium isotopes
Okay.
and study, how they behave.
Okay, so they're making these very, very fleeting bohrium isotopes. But what can we actually say about bohrium in itself? What do we think it looks like?
Well, you might be surprised to hear that we can make some predictions about that.
Okay.
And that's because of where it sits on the periodic table.
Right.
Bohrium is right below manganese, technetium, and rhenium
Okay.
in group 7, so it's in that same family.
Right.
And based on that, we expect it to behave like a typical transition metal.
So kind of like family resemblance.
Right.
Yeah.
Like if your siblings are tall,
Right.
there's a good chance you're going to be tall too.
Exactly. So what does that, I guess, what does that mean for bohrium?
Well, for example, we expect it to be a solid at room temperature.
Okay.
And should have a kind of shiny metallic appearance.
Interesting. So it's not like some radioactive blob.
Oh, yeah.
It's a shiny radioactive solid.
Right.
Okay. But how can we be so sure about its chemical behavior if it's so hard to study?
That's a great question. And to answer that, we have to jump ahead to the year 2000.
Okay.
When some researchers at the Paul Scherrer Institute did something pretty incredible.
Okay.
They actually managed to study the chemical behavior of bohrium using just 6 atoms.
6 atoms?
6 atoms.
Wow. How is that even possible?
It took amazing ingenuity and very specialized techniques.
Yeah.
So to explain this, we need to talk about what a volatile oxychloride is.
Okay. A volatile what?
A volatile oxychloride.
Oxychloride.
Basically, it's a compound that very easily transitions into a gas.
Okay, so something that likes to turn into a gas.
Right.
Right.
So what they did is they took those 6 bohrium atoms,
Uh-huh.
specifically bohrium-267,
Okay.
and they reacted them with hydrochloric acid and oxygen.
Okay.
And this produced a volatile bohrium oxychloride.
Okay.
And here's the brilliant part.
Oh.
By comparing this compound to the oxychlorides of technetium and rhenium,
Okay.
those lighter relatives in group 7,
Right. Right.
they were able to confirm that bohrium actually acts just like we would expect a member of group 7 to act.
So they use this tiny, tiny, tiny amount of bohrium, a compound that likes to become a gas in a comparison to its relatives.
Right.
And that's how they figured out its chemical personality.
Exactly.
That's incredible detective work.
It really is.
Now, I do remember you mentioning earlier that relativistic effects come into play with superheavy elements.
Yes.
I mean, what are we talking about there? What is that?
So the electrons in these heavy atoms are moving around the nucleus at speeds that approach the speed of light.
Uh-huh.
And that leads to some really bizarre behavior that we don't see in lighter elements.
Okay, so things are getting a little mind-bending here.
Yeah, we're getting into some really weird stuff.
Like, what kind of bizarre behavior are we talking about?
So, for instance, some studies have suggested that bohrium might actually defy expectations when it comes to its electron configuration,
Okay.
and that it might give up an electron from its 6-spin orbital before its 7s orbital.
So not exactly behaving as predicted based on its lighter siblings.
Exactly, and this is what makes studying these super heavy elements so fascinating.
Uh-huh.
They're really pushing the boundaries of what we understand about chemistry.
So they're kind of like the rule breakers of the periodic table.
Yeah, they're always challenging our assumptions.
So where does this leave us with bohrium then? I mean, we've got this radioactive shiny element that's not quite following all the rules.
Right.
What's the big takeaway?
I think the big takeaway is that even in the realm of these super heavy synthetic elements, the fundamental principles of chemistry, like periodic trends, they still have a really powerful influence.
Oh, okay.
But there are surprises.
Right.
And that leads to a bigger question.
Uh-huh.
What happens as we create even heavier elements?
Right.
Do the rules of chemistry eventually break down?
Yeah. I mean, does our understanding of chemistry have a limit?
It's a good question. It really is like
Mhm.
we're at this frontier of scientific knowledge.
Right.
And as we push further into these super heavy elements, these relativistic effects become even more extreme.
Right.
And so you're talking about these electrons whipping around
Yeah.
at these incredible speeds,
Uh-huh.
and they start behaving in ways that we just don't normally see.
It's like trying to apply the rules of checkers to a game of speed chess.
That's a great analogy.
I mean, the basic principles are there, but the pace of everything changes it, changes the whole game.
Exactly. And as these relativistic effects get stronger and stronger,
Uh-huh.
it's very possible that these nice, neat patterns that we see in the periodic table,
Right.
they start to break down.
Uh-huh.
The chemical bonds might form in ways that we don't even anticipate.
So are we talking about a future where we need like a new periodic table? Or like a whole new understanding of chemistry?
It's possible. I mean, think about it.
Yeah.
It wasn't that long ago that the idea of these super heavy elements was just theoretical.
Right.
And now we're creating them, albeit in tiny, tiny, tiny amounts.
Mm-hmm.
But we're seeing that we're figuring out their secrets.
It's like we're redrawing the map of the chemical world
Exactly.
and going beyond those familiar landmarks and into like the uncharted territories.
Right. And the further we go, the more we realize there is to discover. I mean, remember, it was only in the year 2000 that we actually managed to directly study Bohrium's chemistry.
Right.
And that was with just 6 atoms.
With just a handful of atoms. I mean, it's pretty amazing what these scientists can figure out.
Oh, it really is a testament to their ingenuity.
Yeah.
And it makes you wonder, like, what other elements are out there waiting to be discovered?
Right.
What will they teach us about the fundamental nature of matter?
It's both exciting and a little bit humbling.
It is.
We keep pushing the boundaries of what we know, but there's still so much we don't understand.
That's the beauty of science.
Yeah.
The more we learn,
Yeah,
the more we realize there is to explore.
absolutely. Well, thanks for taking us on this deep dive into Bohrium.
My pleasure.
It's been a fascinating journey.
It has.
And to our listener, thanks for joining us. And until next time, keep exploring.